So I will continue today's lecture by discussing what can Martian moon reveal. So as you may know, Phobos and Deimos are way more than just small rocky body, and we'll see how studying their surface properties and their geology and also analyzing sample in the laboratory can help us to better understand their origin. And this is one of the main objectives of the MMX mission. So here you have an image of Mars in the background and Phobos. And you can see that there is a very strong contrast between Phobos and Mars. And in fact, Phobos reflects 5 times less the sunlight than Mars. Moreover, you can see how small Phobos is in comparison to Mars. And in fact, Phobos, the biggest diameter on Phobos is about 27 kilometers, and even lower for Deimos, about 15 kilometers. So in comparison with Mars, which is more than 6,000 kilometers, and Earth, which is more than 12,000 kilometers, you can see how small are those two moons. However, so here on your right, you have false color images, but they highlight some heterogeneity on the surface of Phobos and Deimos, and this is by studying those heterogeneity that we can learn about the origin of the Martian moons and the Martian system. So let's start with Phobos. So one of the main features on the surface of Phobos are impact craters. So on this image, you can see several impact craters, and you can see that they have several size, but also different shapes. And you can also see here the Stickney crater, which is a 9-kilometer crater, which is the biggest one on the moon. Other very interesting features on Phobos are what we call grooves. So those grooves are linear, wide, long, and shallow geological features. You can see here that they were highlighted in wine, showing the very linear aspect of the grooves. And for now, we don't know what they are exactly. We wonder if they are some faults on the surface, like fractures, or if they come from, if they are tracks of rolling boulders, for example, on the surface, or chain of crater. And knowing what they are will tell us information about the property of the moon, because they could be originated from an impact creating some faults in the surface, or they can also be due to the proximity with Mars and the tidal forces that can crack the surface of Phobos. So better understanding the craters and the groove can help us to understand the history and the timing of what happened to Phobos, and also the composition of the surface and the physical property of the surface. So on Phobos, the surface is separated into different color properties. So there are two main terrain, one which is dark and one which is bright. And we still don't know the origin of those two different color units. They can reflect different composition of the soil, but they can also reflect different physical properties like porosity of the soil, or they can also reflect different ages of the soil. So with MMX, we will be able to better understand the color heterogeneity on the surface and their origin, and thus Phobos, like the history of Phobos. So now let's move to Deimos. So Deimos is smaller again and even farther from Mars. And we can see here on this picture that Deimos is way more homogeneous than Phobos. So it has two main geological features, a wide concave feature that you can see here. So you can say that it looks like a crater, like an impact crater, but today we are not sure if it's an impact crater because if such an object, like if an object that big to create such a big concave feature would have um, um, like crash on Deimos, we think now that it would have destroyed the moon. So for now, we don't know the origin of these concave features. Moreover, there is also this equatorial ridge around here on the moon that we also need to investigate further. So scientists also studied the color property of Deimos, and in general, the average color property of Deimos is close to the dark unit on Phobos. However, there is also the possibility that there is also a bright unit that you can see here around the equatorial ridge that I just shown before. And so, again, knowing better the colors of Deimos and the origin of the color heterogeneity will help us to constrain its composition, its physical property, and its age. Moreover, comparing Phobos and Deimos is very important because it will tell us if they have a common origin or if they come from two different processes. And so the MMX mission will explore all those surface properties and all those geological features using a spacecraft containing 7 scientific instruments for remote sensing observations. So, for example, we will obtain global information about the composition, the color property, and some high-quality images to better understand the geological features. Moreover, there is the rover, which will land on Phobos. So it will be launched from the spacecraft from about 40 meter in high. And this rover contains 4 scientific instruments for in situ measurements. So this means that the rover will take measurement from a very local place on the surface of Phobos, and it will be direct observation very close to the surface. And the rover will bring more information about the physical property of the surface. Also, when we will study the path of the rover on the regolith. But we also mentioned that MMX will collect some sample and return sample back on Earth. So for that, MMX will land on Phobos, and MMX will stay about like 2.5 hours to collect more than 10 grams of materials on Phobos surface. And for that, MMX will use 2 different sampling approach to probe the surface at different depth, allowing an optimal scientific analysis of the sample. In fact, so the P sampler that you can see in red will bring surface from the very, very top layer on Phobos. And on these top layers, the material may have been modified by interaction with extreme environment like solar irradiation, for example. So we don't necessarily collect endogenous and primitive material, but we collect a transformed material. So to better understand the origin of Phobos, it's very important to have material which is as pristine as possible. And so this is what the C sampler will do by digging a bit in the surface and bring sample from below this top layer. And so bringing sample will allow us to obtain proof of result obtained with remote sensing and in situ observation. And they will clarify some potential ambiguity that we can find during the data analysis of the rover or spacecraft data. And they will bring precision not achievable via the present generation of robotic planetary exploration. So how will it work? So MMX will collect the sample and put them into the capsule, so the return module. So here you can see the capsule. And then the capsule containing the sample will separate from MMX spacecraft. Thereafter, the capsule will start its journey for re-entry to the Earth. Then from Earth, it will be possible to see a fireball visible in the sky when the capsule will re-enter the Earth atmosphere. Then the capsule will arrive in Australia. So here, of course, it's not MMX, it's images from the Hayabusa and Hayabusa 2 mission, but it will certainly works with a similar process. So once the capsule land in Australia, we will collect the capsule with the samples, so they will be safely and carefully recovered in Australia. So you can see here that the person touching the capsule is in a protective gear. This is because the parachute will be released using pyrotechnic explosive, and there is a possibility that not all the explosives had gone off. So just to be careful, the first person touching the capsule has to be in a protective gear here. So once collected, we have to transport the capsule and the sample from Australia to Japan. So, and especially to ISAS, where the curation facility is at JAXA in Sagamihara. So here you have a photo. It's the transportation from Hayabusa mission, and it was at the Haneda airport. So the team has a time limit to transport the capsule and the sample because we want to avoid as we can the atmospheric contamination on Earth. So we want to do it very fast. And for example, for Hayabusa 2, I think the team took like 60 hours to bring the sample from Australia to the laboratory at JAXA. So then scientists will open the capsule under vacuum. And here it's the example of the Hayabusa 2 mission. So here you can see photo of grains. So grains will be selected for a first screening, which is non-destructive analysis. So we will check the size, the shape, and the weight, for example, of grains. Without any technique which could change the pristine of the sample. And here in the video, so I will show you a quick video. So you can see a video of a scientist picking up a particle. And so tools are suitable for handling sample from a few hundred micrometers to a few millimeters. And maybe I can put it again. So we use vacuum tweezers. So it's the most frequently used tool, and they operate by adhering samples to the tip of a straight tube via a suction force. And this is how we can move the grain from a sample order to another one, for example, or to instrumental setup for analysis. And then, so after the first non-destructive screening, some additional measurement will be performed in Japan, but also in other laboratories across the world, according to some scientific objectives. And so you wondered, so what do we actually do in the laboratory? What do we measure, for example? So laboratory analysis unlocks information impossible to obtain in space using high precision instruments and methods. For example, we will analyze the mineralogy of the samples, and according if we find proof of interaction with water or mostly no interaction with water, or if we find proof of high pressure, like high pressure signature within the sample, we will be able to classify our sample. So is it coming from a capture asteroids scenario, or is it coming from in situ formation, which is giant impact scenario? Moreover, if it's a capture, does the sample come from the outer part of the solar system or the inner part of the solar system? We will do also chemical analysis of the sample. For example, we will look at if the sample uh, is rich in elements that evaporate easily or poor in those type of elements. And we will also see if there is a Martian-like composition maybe, or also trace of the possible impactor materials. So according to what we will find, we will be able to classify the grain and better understand the origin of the moons. And another technique that we use on Earth, which was very important to reconstruct the scenario of the formation of the moon on Earth, I mean the moon of the Earth, is isotope analysis. So first, let's focus on the last line of the table. So we will analyze isotopic information of the sample, and it can help us to know if the sample is primitive, so carbon-rich maybe, and come from a carbon-rich meteorite, or if it's more coming from a rocky, less primitive meteorite, or if it's a Martian and impactor material signature. And on the graph on your right, so please don't focus on details on this graph, but it's just to show you that using isotope that you can see on this graph, we can put our sample in such graphs and better understand if they come from outer part of the solar system, if they have property close to a carbon-rich primitive meteorite, for example, or if they come from the inner part of the solar system. So this is a very precise analysis, and it can help to confirm what we obtain with remote sensing and in situ data, or find new information. So now I want to mention what do we do in preparation for MMX, because so MMX will be launched at the end of the year, at the end of 2026. So then what do we do in preparation? What is needed for an optimal interpretation of the data? And there are many things that we can do waiting for MMX. So Phobos has no atmosphere to protect it from the solar irradiation, for example. So we wonder how does solar irradiation influence the surface property of Phobos? Because what if it biases our analysis when we will study remote sensing data? And for that, we do experimental works. We use some simulant of Phobos, so basically powders formed with different minerals that we think can be close to what Phobos is. And then we perform artificial irradiations in the laboratory. And then we analyze how the property of the simulants change along the irradiation. And it can help us to say, okay, so on Phobos, the property should be of this type, but then due to the solar irradiation it can change, and we need to consider this to understand the data, and so to retrace the origin of the moon with no bias, without being biased. And also, so the study of the Martian moon will help us to better understand important questions, so including the origins. So when we talk about the origin of life, we usually think about planets, Mars, Earth, for example. But life does not start with planets, it starts with ingredients of life, which are water, liquid water, energy, chemistry. And asteroids and small bodies may have delivered those building blocks on Earth, like water or organic molecules early in the solar system. And MMX will help us to understand the transportation of those ingredients of life in the solar system. And Mars may have been habitable in the past, but lost its habitability. And some of the information could be preserved in the moon. Yeah, in fact, so Phobos and Deimos are made of primitive material, and they have remained largely unchanged for billions of years. So this is also why Phobos and Deimos may not host life themselves, but they may tell us how life becomes possible. And yeah, so in conclusion, so the study of Phobos surface combined with laboratory analysis of return sample material will reveal the composition, color, geological, physical properties of the moon. So this is why we are very interested in studying their surfaces. And this information will help to trace the origin of the Martian system, which will clarify theory about the formation and evolution of planets in the solar systems, as well as the mechanism of matter transportation in our solar systems.